So now let's go to the third talk. Please welcome Dr. Afshin Dehghan. He's a senior AI/ML manager at Apple. He leads the team behind key multimodal perception features like Face ID, the 2D and 3D Always One engine, Vision Pro, and Rooms Plan, which is the LiDAR-powered 3D floor planning, which has achieved like a lot of traction. His group is now pioneering large model-driven applications that blend visual, spatial, and contextual data for more intuitive user experience. Dr. Afshin earned his PhD degree from UCF in 2016. So now, and today's his keynote title is Advancing Video Understanding from Training Feed to Streaming Video LLMs. Sure.
Cool, perfect. Okay, awesome. Thanks for the intro. I'm gonna try to keep this presentation a little bit kind of concise and focus on three main work that I want to talk about today. The gist of it is I want to first talk a little bit about how much we can push an image-only VLM to solve video problems. Back in 2014, we released this technical report on slow, fast lava. I'm going to be mainly covering the work that we did back then. That is about how much we can push this image-only VLM to solve video tasks. Then how much actually we can squeeze out of these models when we start fine-tuning them on video. Basically, if we take that architecture that wasn't trained on any video data and now we fine-tune it on video, how much improvement can we get out of it? And another topic that I'm very interested in recently is the streaming video LLMs and how we can actually use this VLMs or video LLMs to solve streaming tasks. And we recently have done this work called StreamBridge that I'm going to try to cover that within the time we have. Okay, we've heard a lot about video LLMs today, and if we have a multimodal LLM that has been trained on a lot of text and image, one way to solve a video problem is to just take video frames and start giving them to this decoder LLM, encode them one by one, and just feed them to an LLM and give a query and try to get an answer. I think this is an effective approach, and a lot of the models can handle this to a very good extent. Maybe some of the state-of-the-art model that are commercially available also work this way. But you can do this up until certain frame and up until certain resolution, right? I mean, because your context window is limited and you're going to start hitting some context limit, you have to downsample your images if you want to go over longer videos. So it comes with some limitations, and you're going to lose some, fine-grained special details, especially if you are downsampling your images. So this doesn't seem to be a super effective way, especially if you want to solve some longer video understanding problems. There was several techniques introduced back in 2024 to solve this problem. One of them that we're going to be covering and comparing against is the work called PLAVA, that they do this very smart pooling to reduce the number of tokens that are being fed to an LLM. This worked to some extent, but might not be the most effective way of doing it. Or we can introduce some more smart way to learn the tokens that we want to feed to LLM instead of just doing pooling. One way to do this is using QFormer that was, again, famously used in BLIP2. That is, again, a smarter way of doing it, but you're introducing this additional learnable tokens that comes with a cost. But can we do this better? What we tried to do in Slow Fast, that was also very much inspired by, I don't know, probably most of you are familiar with the Slow Fast work of Kemming, Jitendra, and Christoph back in 2019 for solving activity recognition problem, very similar. We were pretty inspired to see, okay, can we adopt very similar architecture and into video LLMs? So taking on that work, we extend and came up with this very simple architecture where we introduced this two-stream pipeline, and we try to take a video and take a subset of frames from this video at high resolution, but low frame rate. We call this the slow pathway. But we also subsamples a lot more frames, but at a much lower resolution. We call this the fast pathway. And we try to combine all of these things, all of the encoder tokens from these two pathways, flatten them, concatenate them, and then feeding them to an LLM. So this showed to be extremely effective, and it allowed us to actually process videos at much greater length and capture both the special details that comes from the slow pathway, and at the same time be able to feed videos that are much longer because we have this a lower resolution pathway, and we can feed a lot more frames into this. And we saw some very encouraging results that I want to show here. This is the comparison that we did with the 7B model on an open-ended video Q&A across 4 different benchmarks that at a time were quite popular. Here we also compare with methods that do some SFT. Basically, they are not training free. They're not just using the model without any additional training, which SlowFast is doing. You can see Video Lava and P-Lava, the 2 methods. I talked about P-Lava earlier. And you can see that you don't really need to train if you want to outperform some of those methods in certain benchmark. And this very simple strategy of doing this 2-stream works better than some of the SFT methods. And we also compare with some other training-free methods like the image grid, that even comparing with that, we get some very encouraging results that I'm showing here. So this was the open-ended video Q&A. We also compare with some of the multiple choice video Q&A problem, again, on the 7B parameter models, and the results are also pretty encouraging. So this was okay. This seemed to be working pretty well. Then we wanted to take this to next step, and we said, okay, what if now we throw in some video data into the pool? So that was completely training free, the previous work that I showed. And you saw that the results were pretty encouraging. But what if we start now fine-tuning models? What if we have access to a bunch of image data and video data that we can fine-tune this? What is a good fine-tuning recipe here, and how much more juice can we squeeze out of these models? So again, the architecture is very similar to SlowFast that I showed earlier, but what happens here is that the LLM and also the projection layers are being fine-tuned. But the same process again, we take the input video, it goes through a visual encoder that is frozen. We have a projection layer, we have the slow pathway that extracts a lot more tokens, but at much slower frame rate. But we also have the fast pathway that gets a lot less token, but at much higher frame rate, concatenates them together and feed them to LLM that is fine-tuned. Another thing that we did in this work was we wanted to come up with a more simple training recipe. Can we actually minimize this number of training recipes and only use the public data sets that is available, and how much we can get out of that? So the training recipe that we use in SlowFast 1.5 is pretty simple. We have a warm-up stage that is focusing on image understanding. We don't do multi-stage image understanding training. We don't have continuous pre-training. It's pretty simple. And we don't use some of the techniques like image splitting for improving the text-rich quality of the model, etc. Again, one stage, warm up, improve the image understanding capabilities as much as you can. And the stage number 2 is going to be focusing more on handcrafting the right data mixture for video understanding without losing quality that we already warmed up in the first stage. So with this just 2 simple stage of training, now we can see that the results are a lot more competitive. And so specifically for smaller model sizes, here you can see the results for 1B models on several benchmarks. We have the general video Q&A, and we also have the long video understanding tasks. You can see the comparison between SlowFast level 1.5. We have 1.2 in TurnVL and Apollo that we are comparing against. And again, the results were quite compelling, especially for 1B models. The story stays to be similar as we increase the model size, we go to 3B. Still, the results look quite competitive. Same going to 7B. So from 1B, going to 3B and going to 7B, and you can see that we consistently keep improving the numbers on these benchmarks. That kind of shows also the effectiveness of the dataset recipe that we have chosen. I mean, it's always fun to look at some qualitative results as well. Here's an example where, you know, we have this person that is drawing, uh, that is doing this drawing, and we ask the model to describe the video in details. And you can see that pretty much we're capturing all the fine-grained details that has been shown in this image one by one. I highlighted some of the pieces and entities that, you know, has been involved in this drawing. Of course, it's not a super complicated drawing, but it's still a good example to showcase the different elements that are captured in the response. Another set of tasks that we show results earlier were the kind of VQA type tasks. Here's another video where, you know, now we are prompting the model with different set of questions, and the model is responding to the question. Again, the first one is describing the video in details. You can see that the model is again picking up on a lot of the fine-grained details and the entities that are happening in the video. Like, you know, imaginable play in a toy kitchen setup, talking about the toy knife, the cutting board, and, you know, talks about the fact that the user washes the hand and all the steps in order as it happens in the video. We also have questions that, you know, talks about what happens. Sorry, I have my video covering this. Let me move this around. What happens after the person washes the toy fruit? You know, after washing the toy fruit, the person arranges them on a white plate and then cuts them with a toy knife. And how many toy fruits are in the video? And again, you can see that the question is responded with exact details about the fruits that are presented in the video. I also have one more example to show, which I'm actually fond of, which highlights a little bit of a text-rich and text understanding capability of the model. Why do I like this? Because we didn't use a lot of the tricks that are common for training this VLMs to be really good at understanding text. And, you know, the model is still capable of picking up the details and the text that has been shown in the video. For example, the question here is, according to the video, if I want to sign the paper, Tyler is so fast, what should I do? Showing you the steps that is presented in the video, and then the question about the full name of the paper and also the author list. You can see a little highlighted issue that we named in the paper that I see if I can pause it there. Let's see, we're gonna get there in a sec. Yeah, so you can see that the Hongyu has been spelled differently in the article that the model has responded. So that's the error that I wanted to highlight. Okay, so this was about the slow fast 1 and slow fast 1.5, which talks about, okay, long video understanding, video Q&A in a form that a lot of us are familiar with. But there's a series of new tasks that we are specifically very interested in along the line of streaming video LLM. So here the motivation is then why do we need this? Is that in a lot of the cases, in a lot of the scenarios, if it's robotics, if you want to build an assistant, you need the model to have this multi-turn conversational ability, meaning that you want to be able to converse as the video is happening, ask questions, get answers, etc. So in order to be able to have this model do this, I mean, is there any effective data set out there that we can use? How do we build that data set? And do we need to do any specific fine tuning to make that model to be able to do this multi-turn set of conversation and have this dialogue and interleave video text scenarios? Another set of tasks that comes with the streaming video understanding is the proactive assistant, where you prompt the model in the beginning, but then you ask the model for guidance in a specific task, and the model needs to figure out when to respond. And you know, this is not that you ask a question and you get an answer. You might ask a question in the beginning, hey, show me how do I cook this food? And then throughout the time, you get a response based on the action and the visual content that is present in the scene. So that's what I refer to as proactive assistant, where there's a question present in the beginning, you provide a video segment to the model, and the model decides whether or not to provide an answer based on the question. So how do we go and build this? The path to streaming video LLMs, I highlighted 4 different steps that I think is important. The first one is that we need a buffer to manage the incoming frames, and we need a compression strategy because, first of all, you're dealing with a lot of frames in streaming videos. Even the length can be infinite. The video can keep coming. You might want to monitor something for hours and hours and hours. So you need a very efficient way to first buffer the frames that matter, and you also need to be able to compress them in an efficient way to fit that buffer limit. Then we need an activation mechanism for proactive responses, meaning that the model needs to understand when to respond based on the query that it's been provided, right? So you're not asking a question and the model is immediately providing you with a response, but there needs to be an activation mechanism. And we also need potentially some data sets for SFDing and improving the quality of the model in diverse streaming scenarios. So looking at these 4 things, that's what we try to kind of come up with a modularized design in our first work called StreamBridge that I'm going to be covering in the coming slides. Okay, so this is how StreamBridge work. I'll try to make it pretty simple with this set of slides that I prepared. You can see that we have an incoming frames coming as the user is performing a task. And as the frame come in, we start encoding them one by one, and you keep them in a buffer. And then let's say you have a query that is posed at a time t, and then the frame keeps coming and you have the query, but now we have this activation module that needs to decide based on the frames in the buffer and the query whether it's time to answer. And this activation module is nothing but another VLM. It's a very small VLM. It's based on the Llama 1 Vision 500 million parameter model where we replace the head with the binary classification head trained on a large set of data. And all it's doing is having this binary classification that decide, do I need to answer or should I wait? So in this case, for example, at frame 4, and the input to the model is actually just 1 frame. We can optionally also provide the previous frame if it's available. And the model kind of decide, okay, in this case, I don't need to answer. Here, I need to wait. I again don't need to answer. But comes frame 6, and the activation model is triggered, and the model needs to provide a response. And here is where we kind of take all the frames that we have in the buffer. Now we need to decide whether we can pass all of them, whether we had hit some max limit. So we have his round decayed compression step before feeding the input to the LLM. So again, the activation model is a small VLM. The round decay compression is basically checking the number of tokens that we have in our buffer against a threshold. And if you're hitting that maximum threshold, we start getting the earliest frame in the conversation and doing this average pooling to hit again the limit that we have in the buffer to before passing this to the LLM. Let's see if I missed any details here. For training this activation model, it's again, as I mentioned, it's a very small VLM. We tailor this data sets where we have the question, we have the video, and we have the answer. So we, in order to get this binary labels for a majority of the frames in the beginning of the video, we force the model to not provide any response. And only toward the end, we set the classification label to be 1. And that's how we trained and we generated this large data. Wanted to kind of bring this activation model inside the VLM itself and try to like make the VLM to learn when to respond, because sometimes you can actually degrade some of the capabilities of very strong VLM that you already have by trying to like bring this activation module learn directly inside your foundation model. So having this separately, it makes it pretty modular. And you can see in our results that we kind of plug and play this into a lot of backbones, and we show that you can consistently improve the results and not regress on generic video benchmarks. Okay, I see a little, it looks like that my Zoom got disconnected. Okay, let's try to reshare again. Okay. I don't have a lot of slides left, but let's talk a little bit about the data set. So we also introduced this data set called Streamit. We focused on two different tasks for this data set. One of them is this proactive assistance, where we have the question, we have video segment, answer, video segment, answer. So this is the format of the data set. And the other one is Stream Q&A, which again provides this multi-turn Q&A data sets that you have a long video, you have a question, you have an answer, which we think the community was missing. So this is 120K videos. It's constructed from tens of millions of videos publicly available. So the way that we did it was we took all these videos that comes with a caption. We computed a similarity score between the video and the caption themselves, and we filtered about 1.3 million videos that have very high similarity between the caption and the video clip itself. Video clips are roughly about 12 seconds. And then we also computed the similarity across all the video clips. And for videos that are very similar, we start kind of stacking them next to each other. We also have caption for each of those segments. We use a GPT to generate diverse set of Q&A, and we use some rules to kind of keep some questions or drop some questions or create this gap and delay in responses for certain clips to generate some of the proactive scenarios in order to train the model. Now let's have a look at some of the results that I want to highlight. So here you can see two benchmarks. And what I want to highlight here, again, adding StreamBridge with some of the strong VLMs out there, we can do a lot better in these benchmarks. So you can see that we have the Oryx, we have Lava, we have Quen, and when we add this the StreamBridge on top of that, you consistently improve their quality across these two benchmarks that I've shown. StreamBench is the benchmark that we just talked about, and we also have the OVO bench. And we also have another benchmark here. Again, shows that we add StreamBridge in two other benchmarks, the dense video captioning and the SLC. And again, we improve the quality. Another thing that I want to notice is that once you train the model with this activation module on the Streamit dataset, we still keep the quality of the model to be the same, if not better, on other previously explored video LLM tasks, which we have shared a lot more ablations and results in the paper. I think we're almost at time. Want to leave some time for questions as well. Thank you.
So if you have any questions from Zoom, they can directly unmute and ask, and anything from the auditorium as well. Yeah, go ahead.
Thank you very much for the great presentation, first of all. I have a question regarding the slope of Java version 1.5. So I had a chance to read this paper. I mean, that's a paper. According to paper, they're sampling the videos at 1 FPS, and maximum number of frames that they're utilizing is exactly 128. That roughly translates into like just over 2 minutes of videos. So my question is, what do you think, like, how can we modify this architecture to handle like relatively longer videos, let's say like the videos that are over 10 minutes and so on, considering that we have limited context length. I know my question is connected to the work that you described later, that is the streaming of the video. But in the streaming setting also, we are using round decade compression. Again, we are trying to convey a notion that the latest frames are the most important, and that is where we are sampling. But let's say if we have to sample like more context, like more number of frames, what do you think how we can do it? And the last question, the second question, the connected is did you get the chance to test these models on like mobile devices as well? And how do they perform on the mobile devices? Thank you very much.
Question. Great question. I think the limitations that you referred to, I think, are pretty known limitations, right? I mean, and you know, we have the context length limitations, we have the resolution limitations. We also at the same time want to process long videos. The first question that I ask is, why do we want to process long videos? What do we want to do? What is the task that we want to solve, right? I think there is probably arguments for wanting to process a 5-minute video, 10-minute video, hours-long video. Do we want to process it at once, or do we want to process it in chunks? Do we want to kind of find correlation between the first frame and frame number 1 million? I think this is a big challenge that we need to like kind of figure out. And I'm sometimes like are not super convinced that we really, this is the problem that we need to solve, and we need to go toward trying to like address a very, very long video problems. But at the same time, if there's compelling use cases for it, we should. The context window of this LLMs are consistently growing. You know, we can even have a, you know, kind of infinite context window. The models that we have available publicly that we can play around with still have very limited context window. And this is where the research is trying to like scramble to like fit everything within 16K, 9K, whatever the context limits of the models are. But again, we all know that this might not be the limit in near future, and you might be able to like fit a lot more frames into the models. I think that is one line of research that is growing. And I think it is not necessarily limited to the video LLM processing. So I'm not sure if this is really something that we should try to solve or we should try to address. I think one thing that we can research is how much we can, within the context limit that we have, we can squeeze in terms of quality, and how much can we fit by keeping the spatial resolution and, you know, the frame rate and understand within this limit. And I do believe that, you know, the context window problem is something that the industry is moving forward. It's going to get resolved sooner or later. And as these models get better, we also will get access to more context windows. On some other tasks that you mentioned, running this on mobile devices, the problem even becomes more dire. You know, the context limit of models that run on device are even smaller. We need to get a lot more, you know, smart about processing those videos. And to be honest, I don't know of an effective ways of doing this for very, very long videos. But the problems that we are also interested in solving on mobile devices might be more closer to streaming video, or, you know, providing like processing smaller set of videos. So that was the second line of work that we just talked about. But you're pointing out to the problem that I think it exists, and I think that's my view of how I see this is going to be evolving in the next few months or a couple of years. Yeah.
Thank you very much.
No worries. Yeah. Awesome. Thank you.
Oh, we have one more question from the audience.
Oh, one more. Okay.
Thank you for the presentation. I have a question, not a few minutes, but for the stream bridge model, when an activation module activates and answers, is the memory buffer flushed? And if it is, like how, like what if they would ask the same question again? Would have to do that wait for another?
So the memory is not flushed. Actually, when you answer the question, the answer is also been appended into the buffer. So you both keeps the visual history and use the text history. Maybe like the slide that I had, sorry, this is just a little bit slow. It's not exactly showing it, but the details been shown in the paper. So when we answer a question, the memory is not flushed, and the actual answer of the model is also being appended into the memory. So you kind of keep a history of the answers that the model provide and the question that the user had asked before, along with the visual information. So the memory has only been kind of addressed when we hit the limit or the max number of tokens that we have in the.
So another quick one. So the activation model might be a misunderstanding. It decides whether or not it needs to answer based on what the question and the number of frames that are inputted. But like, what if, let's say, and we're just asking a question that's in the distant past, like in the past, and what if they have to rely on future frames? So again, whether it will be able to use past frames.
That's a good question. I don't know if the current data sets that we have experiment with something like this. But one thing to note is that we are not necessarily dropping frames or completely forgetting them. In the round decay compression that we also have, we use an average pooling of the earliest frame and the most recent frame to address the memory problem. But I'm not going to be surprised if we can answer questions way in the past that the model has not already captured the visual information in the buffer. So you're raising, again, a limitation that, again, I don't think we have stress tested it. I do suspect that if the average pooling strategy is going to keep the history to some extent. But again, it really goes back down to, how long the video is, the question. But usually in streaming videos, you want to interact or you want to give user feedback about what's happening right now. You want the user to kind of understand what's happening right now. So it's not really a problem that you want to address, like and the user asking a question far in the past. I don't know if this is going to be very relevant for this task.
Thank you.
Of course, thank you.